Slow-motion 4K footage of F-16C/DS flaring and touching down at Palanquero Air Base, Colombia. Wheels smoking, afterburners glowing orange. Cut to archival 1970s wind tunnel footage and early F-16 test flights. Dramatic music sting. Imagine this. You design a fighter jet so aerodynamically unstable that, without computers reacting hundreds of times per second, it would tumble out of the sky in under a second. That isn't a design flaw. That's the entire point of the F-16 Fighting Falcon. In August 2025, a squadron of these American Vipers from the South Carolina Air National Guard's 169th Fighter Wing landed here, at Palanquero Air Base in Colombia, for the Relámpago de los Andes exercises. They came to train air-to-air combat against Colombian KFIR jets. On paper, it looks like routine military cooperation. In reality, it's living proof that engineers solve one of the hardest problems in aviation. How do you make a fighter that turns tighter, accelerates faster, and still lands safely on almost any runway in the world? Map animation, showing flight path from South Carolina to Colombia. Overlay of geopolitical context, regional tensions, drug interdiction, interoperability needs. Cut to Colombian KFIR and US F-16 formation flying. The driver isn't hype. It's physics and strategy. Modern air combat is about energy management. Who can sustain speed and altitude longest while maneuvering? Colombia's aging furs are fast but bleed energy in turns. The U.S. wanted to test its jets against a real opponent in a realistic environment. More importantly, forward deployment like this proves the F-16's greatest engineering achievement. It doesn't need a U.S. carrier or a massive dedicated base. It can operate from Allied airfields halfway around the hemisphere with just aerial refueling and AC-17 support package. Animated force diagrams. Show center of gravity, CG, versus center of pressure, CP. Split screen. Stable aircraft trim drag arrows versus unstable F-16. Wind tunnel smoke visualization of airflow. Here's the first principles problem. In any airplane, lift acts through the center of pressure. For stability, the center of gravity must sit ahead of that point. Like a dart, the natural restoring moment keeps the nose pointed forward. But that stability costs you. Every correction creates extra drag. Fighter pilots don't want stability. They want to point the nose instantly anywhere. The solution? Move the center of gravity behind the aerodynamic center. Now the jet is unstable. A tiny disturbance and it wants to flip over. This is called relaxed static stability, RSS. On the F-16, the static margin is negative. Without intervention, it is unflyable. Why do this? Because instability reduces trim drag dramatically. The jet naturally wants to pitch up. Exactly what you need in a dogfight. You get higher sustained turn rates and better instantaneous pitch response. But now you've created an impossible control problem. The pilot can't react fast enough. The laws of physics demand a machine that can. Exploded 3D CAD model of F-16 showing flight control computers, actuators, and quadruplex wiring. Real cockpit footage of pilot inputs. CFD simulation of leading edge route extension, LERX, vortices at high angle of attack. Side-by-side F-16 versus conventional jet turning. Enter the world's first production digital fly-by-wire system. For independent computers, quadruplex redundancy. Read pilot stick inputs 40 times per second and command the control surfaces before the pilot even feels the instability. If one computer fails, the other 3 voted out. This isn't software magic. It's solving differential equations of motion in real time. \Q equals F \alpha \delta underscore EV, where the pitch rate is continuously corrected to keep the jet exactly where the pilot wants it. Add the leading edge route extensions, those strakes ahead of the wings. At high angles of attack, they generate powerful vortices that keep airflow attached over the wing long after a normal wing would stall. That vortex lift gives the F-16 insane maneuverability above 20 degrees angle of attack. Combine that with a Pratt & Whitney F-100 afterburning turbofan, pushing thrust to weight above 1:1, and you have a jet that can pull 9G turns while still accelerating. Result? The F F-16 can outturn almost anything in its class at medium altitudes and speeds. Graph of specific fuel consumption, military power versus afterburner. Maintenance bay footage showing avionics access. Cost per flight hour comparison table. F-16 $25K versus F-35 $35K plus. But nothing is free. The afterburner is thirsty. Specific fuel consumption jumps from 0.8 to over 2.0 lb/lbf/hr. One high-G engagement can burn hundreds of pounds of fuel in seconds. The fly-by-wire system is maintenance-intensive. Those computers and actuators need constant checking. And while the jet is cheap to buy, especially upgraded Block 5052S, operating it still costs real money. Colombia looked at the numbers, considered sustainment costs, industrial offsets, and chose Saab's Gripen instead. The Gripen is lighter, uses less fuel, and offers better availability for the same mission set. The F-16 wins on raw agility and proven numbers, over 4,500 built. The Gripen wins on operating economics. That's the trade-off every Air Force must accept. Slow-motion landing sequence with overlaid runway length, approach speed, 130 knots, and ground effect visuals. Palanquero Air Base specs overlaid. So, why could these jets land safely at Palanquero? The same unstable design that makes it agile also gives precise control on final approach. The fly-by-wire keeps the nose perfectly stable even in gusty Andean winds. Short takeoff and landing performance, around 1,500 feet ground roll with afterburner, means it doesn't need 10,000-foot runways like older jets. Support aircraft C-17s, KC-135 tankers handle the logistics. The F-16 itself is designed for rapid turnaround, minimal ground crew, built-in auxiliary power unit, and modular avionics. Side-by-side F-16 versus Gripen versus F-35 cost and capability charts. Montage of F-16s in service worldwide, Ukraine, Taiwan, Middle East. Is the F-16 still viable in 2026? Absolutely. For now, it's not stealthy. Its radar cross-section is measured in square meters, not square centimeters. But upgraded AESA radars and modern missiles keep it lethal in beyond visual range fights. Cost per flight hour remains competitive. The U.S. will keep flying Block 7072 Vipers for decades because they already exist in huge numbers and the supply chain is mature. But the Colombia exercise also showed the limits. When a nation like Colombia weighs long-term ownership cost against agility, newer designs can win. Beautiful wide shot of F-16 climbing into Colombian sunset. Text overlay with sources and subscribe for more first principles engineering. The F-16 proves that sometimes the best engineering solution is to break the rules on purpose, make it unstable, hand-control the computers, and let physics do the heavy lifting. Human ingenuity doesn't defeat the laws of nature. It finds the clever loopholes nature left us. And that's why, 50 years after its first flight, the Viper can still show up anywhere on Earth and dominate the sky. Thanks for watching. If you want the deep dive on why Colombia ultimately chose a Gripen, let me know in the comments. Like, subscribe, bell icon, suggested next videos.